Hi, good to meet you. Hi. Sorry. Oh, no worries.
Hi, Larry. We need some adapters. Do you have? Perfect.
Last comes out to be that Amy put one.
Okay.
Oh, both adapters out in the basket or something.
I need a t-shirt from you.
Yeah, he wants to because he has a prediction on the back of your t-shirt.
Where did you get it? eBay, okay.
Oh,
Let's take our seat, please. Before I turn things over to Josh Frieman for the afternoon, first panel of the afternoon, there are a couple of announcements. This evening will be the reception and banquet. It will be held on campus, about 59 blocks south of here. You can still pay online. You can see Amy immediately. She has to know how many dinners she has to cook. The buses board at 5:30 and will leave for the leave for campus at 5:45 sharp. If you want to Uber or taxi or get to campus any other way, the address is 5640 South Kellis. The buses will board at 9 p.m. and depart at 9:15, return to the bleacher center. On campus, in addition to EDU Roam, there's a Wi-Fi password for the campus that's in your registration information. Finally, the posters must be removed by 5:30 p.m. tomorrow. The easels will be removed with the posters on them or not. Thank you.
Okay. Welcome to this afternoon's panel session on what is the origin of cosmic acceleration. Just want to, for those of you who were at the boring inflation session this morning, we had a wonderful session up here in the morning on cosmic acceleration. Quite a variety of interesting talks on both theoretical and observational developments, past, present, and future. We're not going to have time to go over all of them, but it was a great session. We have a distinguished panel of speakers this afternoon. Andy Albrecht from the University of California at Davis, Saul Perlmutter from the University of California at Berkeley and Lawrence Berkeley National Lab, and Rachel Rosen, incognito there on the right, from Columbia University. And I believe I'm not violating our code of conduct, where, so these are the mascots for each of these three institutions. So Rory the Lion for Columbia, the Nittany Lions, Oski the Bear for UC Berkeley, and the most puzzling one is Gunrock the Mustang, is the mascot for UC Davis. How many people knew that Gunrock was the mascot of UC Davis? I bet Andy didn't.
So the case for our new theory center is that we're going to figure out.
Okay, very good. Yes.
We hired
Right.
string theorists.
Right. So we're going to have a session tomorrow on the nature of Gunrock. Okay. So in this session, in this conference, we've been talking about a number of things about the standard cosmology that we don't understand, physics of dark matter, the physics of inflation. The focus this afternoon is the physics of cosmic acceleration. Is the origin of cosmic acceleration dark energy, or does it involve some modification of our understanding of gravity? And what do we mean by this distinction, and is it always meaningful? And if it is something like dark energy, is it the cosmological constant or vacuum energy, or is it some new dynamical component? So these are, I think, still open questions in the field. Before turning it over to the panelists, I just want to remind you of some of the evolution of the field over the last 20 years, when a lot of us took notice of this 20 years ago with the results from the two supernova teams, the High Z supernova team on the left and the Supernova Cosmology Project on the right, which both found this evidence for cosmic acceleration from supernovae. So that was the situation 20 years ago. For the students in the audience, this was the first indication, direct indication of cosmic acceleration. And I just want to give you flash up where how much we've come in 20 years. The constraints have gotten substantially better. So we've made real progress, not only with supernovae, which are in green, but the breaking degeneracies with the cosmic microwave background, leading to the very tight constraints shown there in red. Of course, this is just assuming that cosmic acceleration is caused by a cosmological constant. We now, over the last 20 years, have been able to obtain increasingly precise constraints on the equation of state of dark energy. Here's just one example I chose completely at random from some recent survey. Oh yes, it's the dark energy survey, look at that. Just completely at random, and showing that the dark energy equation of state parameters completely consistent with the cosmological constant value of -1. And by combining various data sets, and you can pick your favorite survey or set of surveys, the constraints are now down at the few percent level, assuming a non-evolving equation of state parameter. So this naturally might lead us to ask, okay, should we just say, are we done? It's the cosmological constant, let's go home. I think, and so I think that's one thing we'll be discussing today. Here is just an example. This was shown also earlier this morning. On the left, if you allow the dark energy equation of state to evolve in time, then the x-axis on the left is the current value of the equation of state parameter. The y-axis is WA. That's essentially the time rate of change of the equation of state parameter. Current constraints shown in red. On the right are current constraints on these modified gravity parameters, which again would each be 0 in general relativity. And I would say, so if you're a pessimist, you would say, okay, we live in the boring lambda CDM universe, and the next generation of surveys, just now about to start, is just going to keep honing in on these values. But there is still the possibility that there are surprises just around the corner in the stage 4 projects. So I think it's too early in my book to give up. So one thing we'll be talking about in this session is how we put together different kinds of probes in these cosmic surveys, supernovae clusters of galaxies, weak and strong lensing, large-scale structure. That's, I think, one of the highlights of the evolution of this field over the last decade, is being able to put these together in ways that are mutually reinforcing and give us more robust and stronger constraints. And again, as we heard a nice talk this morning from Chi-Wei Chang, talking about how we're really now at this transition point between the stage 3 to the stage 4 surveys. So it's quite an interesting period, I think, in the history of the field. One thing we should note, though, is that there is more cosmic information to extract from the sky. The stage 4 surveys will be fantastic, but they're not going to measure every single mode of the large-scale mass distribution in the universe. And in principle, there is quite a bit more room there to extract further information and derive even tighter constraints, not only on dark energy, but on other cosmological parameters of interest. So I think the question arises, and this is a plot from the the Cosmic Visions Dark Energy group that Scott Dodelson led a couple of years ago, looking at the case for a stage 5 dark energy program. Obviously, this raises questions of what the cost of such a program could be if things keep going down, looking like this after stage 4. Will we really want to put in hundreds of millions to $1 billion to go to shrink those error bars even further? And there's kind of the George Mallory question. Maybe we should do it just because, like Everest, those modes are there, and we should therefore extract all that information. However, as we learned from Gary Bernstein this morning, there are real hurdles to extracting that information, or at least being able to interpret it in terms of our model. This is just a list of some of the effects that Gary talked about that really, when it gets down to these extreme levels of percent level of precision, you really have to question a lot of the simplifying assumptions that we've been making for decades, which were probably fine for the level of precision that we had, but which may be questionable when we're getting further into the era of hyper-precision cosmology. So I'm not going to, I'll come back to these. The four of us have been discussing a series of questions over the last few weeks. I'm not going to go through these now. I think we'll come back to these after we hear from our panelists their opening remarks, and then we'll get into some questions and then get into a discussion with you. So first up, we're going to hear from Rachel.
So thanks very much. I thought what I would do with my time on the panel would just be to review what are the common approaches to trying to understand cosmic acceleration, what are their current status, and what do I think the interesting open questions are. So in this talk, I think I'm definitely going to be asking more questions than giving answers, but hopefully that will prompt some discussion. So I'm just going to start by reviewing the cosmological constant problem. This is something we've all seen a million times. But just to make sure that we're all on the same page. So what exactly is the problem? I mean, we have this beautiful theory. We have Einstein's general relativity plus lambda. We go out and we make observations, and these observations fix the value of lambda. And then we keep confirming this theory to greater and greater accuracy, barring things like the H0 discrepancy. So what exactly is the issue? We have a theory that seems to work. So the issue is the following. It's that from the point of view of quantum field theory, we actually know certain physics that will contribute to the value of the cosmological constant. So if I look, for example, at just the simple issue of vacuum energy coming from matter leaps. So in this first diagram here, in number 1, I'm considering vacuum production of electron and positron pairs. I know that this diagram couples to the graviton. In other words, the energy produced by these electron-positron pairs gravitates. And if I sum up these diagrams, I get a contribution to lambda, to the cosmological constant. And I know that this value is going to be huge. It's going to be much greater than the value that we've observed. So this is this contribution lambda matter that appears in the bottom. Not only that, but matter loops are not the only contribution that we know of to the cosmological constant. So we know that through cosmological evolution, the universe undergoes various phase transitions. There are characteristic changes of energy associated with, say, the QCD phase transition, or the electroweak phase transition, and these vacuum energies will also contribute to the cosmological constant, and indeed these are also larger than the observed value of the cosmological constant that we see. And finally, 3, so there are also other possible contributions to the vacuum energy. I haven't included anything if, for example, we live in universes that have non-trivial topology. These are things that can also contribute non-trivially to the cosmological constant. All right, so this seems initially like a huge discrepancy. We're predicting something much larger than what we observe. The reason why this isn't the end of the story is that we can include in the total lambda this value lambda naught. So this free parameter that appears in our theory, some bare cosmological constant. And it's really the combination of all of these contributions that lead to the observed value that we see. And so what we end up doing is that we pick this lambda naught to exactly cancel the excessive contributions coming from matter loops, coming from phase transitions, coming from other things. And that way we get the value that we see. But you can argue that this is a very strong fine-tuning. I mean, it's well known, this is many hundreds of orders of magnitude off that we have to tune. And so this is very unsettling. This feels very unnatural. I think it's worth pointing out that the cosmological constant problem is a close cousin of the hierarchy problem that we have in the standard model. So we know that the Higgs boson receives corrections to its mass from loops of massive particles. So here I have a loop of the top quark, and the correction to the Higgs mass is proportional to the top quark mass squared, times some factors 1/16 pi squared, etc. It's a minus sign because it's a fermionic loop. And this is going to contribute, obviously, to the Higgs mass at orders of magnitude comparable to the mass of the top quark. Now, we believe that there should be physics beyond the standard model, which means that if we have massive particles at the gut scale, if we have massive particles at higher scales, these are also going to contribute in a similar way to the Higgs mass. Nevertheless, the Higgs mass we observe is only 125 GeV. So again, we're left in the same situation where we can add some bare mass to the value of the Higgs, but we have to tune this mass incredibly carefully in order to arrive at the Higgs mass that we observe. So said more technically, so both the cosmological constant and the Higgs mass are exquisitely sensitive to UV physics. And when I say exquisitely, I mean that they're power law sensitive to UV physics. So by changing things a little bit in the UV of the theory, I can dramatically change both the Higgs mass and the cosmological constant. And so this is the question that we want to address, is why does this fine-tuning take place? Do we need something other than this fine-tuning? All right, so before launching into the cosmological constant, I thought we should talk about naturalness a little bit too, and what we mean by naturalness, and when has naturalness been, in fact, misleading from a scientific point of view. So this is actually my favorite example of naturalness arguments leading us to the wrong conclusion. So this is Aristarchus, who went around 300 BC. He proposed the first known heliocentric model of the solar system. But Aristarchus observed that he had to explain the absence of observable parallax for the stars. So if you have a geocentric model of the solar system, then you simply say, well, I'm at rest with respect to the stars. But if you have a heliocentric model of the solar system, then you're orbiting around the sun, and you have to explain why there's no parallax. And so what Aristarchus postulated is he said, well, the stars just must be really, really far away. So in other words, there must be some objects close to us for which we observe the parallax, but the stars have to be incredibly far away by comparison. So apparently contemporaries at the time found this hierarchy to be completely unnatural. So what they said is there's no good explanation as to why there should be objects close to us, and then nothing, and then things that are incredibly far away. This is too unnatural, and therefore the solar system must be geocentric. So this is a bit of a warning saying that we shouldn't always trust naturalness arguments. The other thing about naturalness is that we use it very casually sometimes to mean very, very different things, and that these things aren't always equivalent with each other. So we talk about in physics, when is a parameter natural? And usually what we mean by a natural parameter is something of order 1. Now you can say, well, why is it that parameter and not that parameter squared? And well, okay, that's not such a big difference whether a parameter squared is order 1. But you can also start asking, well, why not log of that parameter? Why is it that parameter and not log of that parameter? And without any kind of measure, we don't really have a good reason for discussing these issues. Similarly, we use natural to talk about when a theory is natural. So for example, possible solutions to the hierarchy problem include things like having 10 to the 32 copies of the standard model. Now, this is an incredibly brilliant and beautiful model, you might suggest, a beautiful resolution to the hierarchy problem, but I think lots of people are uncomfortable with it because we don't consider this theory to be natural. We've sort of traded a naturalness of a parameter, an unnaturalness of a parameter, to an unnaturalness of a theory. But we don't really have a terribly rigorous way of discussing these things without having some kind of measure on theory space. So I think it's important to be careful what we talk about when we talk about natural. All right, so moving on to the problem at hand. Why is the cosmological constant in particular so small? And I'm just going to give an outline of the main possibilities, and again, what I think the interesting questions are. So I'm going to focus on a few questions about the landscape, a few questions concerning dark energy and modified gravity, and then briefly mention some other options as well. All right, so as you all know, the idea behind the landscape is that I start out with some underlying theory, say some UV-complete theory of the universe, and this theory could predict a huge number of possible vacua. And in these different vacua, I have different values of constants, including values of the cosmological constant. And the reasoning goes that many regions of this landscape are going to be inhospitable to any type of observer. And so, almost tautologically, any observer should live in a region that's consistent with life. And this would force us to live in a section of the landscape that would have a small value of the cosmological constant. So in other words, the landscape reasoning would say that the value of the cosmological constant is just the result of anthropics in a landscape of otherwise inhospitable vacua. So I think an interesting question is, how do we think about naturalness in the age of the LHC? So in other words, we just turned on the LHC fairly recently. We observed the Higgs as predicted. However, we didn't observe any kind of dynamical mechanism that could explain the hierarchy problem, that could explain why the Higgs has the small mass that it does. And so what is this telling us about anthropics, and what is this telling us about the landscape? Is it an argument, is it evidence for the landscape? So I would say that there's an important distinction between the hierarchy problem and the cosmological constant problem. And that is in fact that natural solutions to the hierarchy problem do exist. So low-scale supersymmetry breaking is a solution that most people would consider natural. It just happens to be that that isn't our universe that we live in. But if I draw this landscape here, so this slide is supposed to depict the landscape, we can imagine a large region of inhospitable vacua. There should be regions where there are natural solutions to the hierarchy problem, and regions where we have a finely tuned Higgs mass. And almost by definition of natural, the regions that are natural should take up more space in whatever this landscape is than the finely tuned Higgs mass. And yet what we're finding is that we seem to live on one of these finely tuned dots. All right. Whereas for the cosmological constant, I would argue that there isn't a comparable picture. We really don't have natural solutions to the cosmological constant problem. Now, there is a caveat with this, which is that if you talk to a string theorist, they might tell you that low-scale supersymmetry breaking isn't actually that natural from the point of view of string theory. And so there's a little bit of a tension. You know, I think if we had found low-scale supersymmetry breaking at the LHC. As particle physicists, we would feel like we were done and that this was a very satisfactory and natural solution. But maybe from a string theory point of view, this is not a natural part of the vacuum that we live in. And so again, I think we need to be careful about what we mean by natural in these contexts. All right, so the second question, which is very much an open question and was discussed this morning, is what is the status of metastable de Sitter vacua in string theory? All right, so if you do imagine that you have this landscape that is populated in the context of string theory, you would technically need, or at least hope to have something approximating a metastable de Sitter vacua in order for these anthropic arguments to go through. But this is very much an open question. So I'm not going to dive too deeply into it, but in 2003, there was a paper by these 4 authors, KKLT, who outlined a construction for getting metastable de Sitter vacua. Since that paper, there have been many objections to some of the arguments and also many rebuttals to those objections. And more recently, in 2018, there was a paper by these 4 authors, including I think 2 of the authors who are here in the audience, who postulated, based on generic string compactifications and the difficulty of constructing metastable de Sitter vacua in string theory, that there's this bound on the scalar potential that would essentially forbid metastable de Sitter vacua. So I think this is very much an open question. Okay, so what about other possibilities beyond the landscape? So historically, another approach that people have taken is they've said, well, let's assume that the cosmological constant is in fact just 0. So let's assume that there's some mechanism, maybe some symmetry, maybe something else, maybe the CC just doesn't actually gravitate, but something that sets the cosmological constant equal to 0. Are there other mechanisms that we can develop that would give rise to late-time cosmic acceleration? And so these go by the name of dark energy or modified gravity. I realize that I use these 2 terms fairly interchangeably. I don't think everybody does. From my point of view, dark energy is something that you would add to the right-hand side of Einstein's equations, some new exotic form of matter that would give you some late-time acceleration, whereas modified gravity would be something that you add to the left-hand side of Einstein's equations. But of course, there's some ambiguity, because you can always move these terms around. More recently, people have come up with sort of an absolute criteria of saying, well, do you have strong equivalence principle violation or not? So if you have a theory in which a strong equivalence principle is violated, you should consider that modified gravity. Otherwise, it falls into the category of dark energy. All right, but as you see, there's this huge zoo of models that have been developed over the last few years. And basically, you can start answering questions. So as we heard this morning, general relativity is the unique low-energy Lorentz invariant theory of a massless spin-2 particle. So if you want to move away from that, you have to start violating some of those assumptions. And so a lot of these theories arise when you start either adding new fields or questioning some of those original assumptions. And so you can ask, well, do we have to have Lorentz invariance? Could we have extra dimensions? Is a spin-2 really massless? Are fields minimally coupled to matter? And so forth. And you get this sort of zoo of theories. And I think the open question is, nobody really agrees what makes any of these models more compelling than any of the other models. So I should say that I think a nice thing about dark energy and modified gravity is that it's falsifiable. We can go out and make observations and rule these out, but apart from observations, there really isn't a consensus as to why one of these models might be favored as compared to another one. I think also an outstanding problem with the dark energy and modified gravity point of view is that it really doesn't solve the old cosmological constant problem. You really have to assume that something else is setting the cosmological constant to 0. If you want to solve this problem in the context of dark energy and modified gravity, it's been argued that these models inherently have to have some non-locality in them. And one way that you can see this is that you can imagine that whatever extra fields that you're adding are acting as a screen, and sort of screening the cosmological constant at late times. But by causality, this also means that a cosmological constant would not be screened at early times either. So really, you would only have a mechanism that works at large distances and at late times in the universe. And in order to have a dynamical mechanism that fixes the old CC problem, you would need to introduce non-locality. Well, once you do that, we don't really know what the rules are. We don't really know what makes a good or consistent non-local theory. And certainly in the context of EFT, sorry, how much time do I have? 6, okay, very good.
So your post, why the non-locality?
Oh, yeah, so you're looking for a screening mechanism that's basically going to screen long wavelength modes, so modes at very large distances. But then this also means that they're only going to get screened at late times. So this mechanism wouldn't work in the early universe. It would only be a mechanism that works, say, in the present age, unless you introduce some kind of non-locality. So certainly in the context of effective field theory, we're not sure what the rules are. There's also a nice point, I think this was pointed out by Justin Curry originally, sorry if I'm misattributing this, but a possible non-local solution to the cosmological constant problem is you can just say, well, let me pick a future boundary condition to be that r equals 0. Done. Like, we're used to picking boundary conditions. This is a non-local boundary condition because it concerns the future. But once I fix this boundary condition, then the cosmological constant is just going to be equal to 0. Now, clearly this is not a very satisfying solution, but then it means what are the rules for other non-local resolutions to the cosmological constant problem? All right, and finally, we might ask, well, what are other options beyond these? So an option that's been around for a long time, which I think is fun to think about, is the idea that de Sitter spacetime itself might in fact be unstable once you include quantum mechanical corrections. So we know that de Sitter spacetime is a stable classical solution of Einstein's equations, but lots of people have argued that it's possible once you turn on quantum mechanics that the cosmological constant will essentially bleed out into particles and reduce the value of the CC. So you should have in the back of your mind, this is effectively like Schwinger pair creation, where if you have a very strong electric field, at a certain point you'll start creating electron-positron pairs. The pairs will move away from each other and dilute the electric field. And the arguments that sort of go in this direction is that there are very close analogs between an observer in de Sitter spacetime and an inertial observer in a Schwarzschild metric. So both of these observers see some thermal temperature. In the case of the black hole, we know that it means that the black hole is evaporating. The question is, could you have a similar mechanism for de Sitter spacetime? And then even if you do have that mechanism, I believe the result is that de Sitter would decay very slowly. And so people have considered more elaborate scenarios where you coupled a certain types of matter that would sort of enhance the quantum mechanical instability of de Sitter as well. So that's one possibility. Another thing that people have looked at is that the possibility that nonlinear cosmological perturbations could backreact on the geometry and give rise to late-time acceleration. Another possibility is that we simply don't have a complete understanding of gravity in effective field theory. I mean, when we do this calculation, and I think this is a bit of a red herring, but when we do this calculation of the vacuum energy, we're doing it in flat space-time. And this calculation tells us that we should really be doing the calculation of vacuum energy in de Sitter spacetime. Now, I think this is all very well controlled, but it just makes the point more generally, maybe there's something that we really don't understand about the unification of effective field theory and gravity. And then, of course, maybe there's something else, something that people have already thought about that I haven't discussed, or something new as well. So just to summarize, I think one of the important questions that we're facing is what is the role of theorists in understanding the cosmological constant problem in the absence of any new data? So if observers and experimentalists keep measuring W equal to -1 to more and more precision, what role should theorists play in this? And I think it's notable that none of the approaches that I've discussed here are technically new. So certainly we've had improvements in understanding, we've had more sophisticated arguments, there are more models that have been written down, but I think if this talk was given maybe 10 or 15 years ago, the major approaches would have looked more or less the same. So what should we be doing differently? And I want to argue that I think it's really important, especially in the context of things like dark energy and modified gravity, to re-examine things like consistency constraints and try from a theoretical point of view rather than an experimental point of view to constrain these theories by things like causality constraints, analyticity bounds, whether or not they admit consistent complete completions, and try and motivate theories better in this way. And to be more extreme, maybe that's not enough, maybe we need some kind of revolution, but I'll stop here. Thank you.
Andy Albrecht, and I think Andy and Saul don't have slides, so
Yeah, I'm just going to sit here and take my notes. So, very nice presentation, Rachel, and I want to. So I just have a few broad reflections to share. First of all, I comment about so there's been some uneasy conversation about controversy and should we be having it? Are we having the right kind? All of this. Controversy is what we do. As scientists, we gravitate toward the unsolved problems, and if it's unsolved, there's different ideas, and come and argue about it. And so, like, what would you do if you got invited to a conference where you were promised that there would not be any controversy? Would you even go? I think. So digging in, I agree with Rachel. We have this very deep unsolved question about why lambda or the vacuum energy is 0 or small. We've really not had great progress on that, in my view. And it definitely, a resolution of that definitely can undermine all the ideas that are kicking around about the acceleration. In addition to that, if we decide we want a rolling scalar field, if that's the idea that's attractive, there's this additional feature, which is the mass scale that goes into that. And just as a point of reference, we can talk about the photon mass. Now, if I ask Rachel the photon mass, she'll tell me it's 0. If I ask Saul, what he should tell me is that it's less than 10 to the minus 18 electron volts, because he's an experimentalist. And his colleagues at LBNL published the particle data group materials, which make that claim. And so by comparison, so 0 mass is the same as 10 to the minus 18 in our theory world, in our experience. And so the typical quintessence model would have to have a mass of 10 to the minus 31 electron volts. And so many orders of magnitude less than 0. So it's a very strange beast. So if we want a rolling scalar field, it's a very strange beast that we're asking for, and we have to deal with the physics, and there's some ideas how that might work, but that's a big deal, what we can expect from that. Now, so I claim there's these big questions, we don't understand them, and if Simon White is here, he's going to say, well, what facts am I basing that claim on? And the facts are how the theory world has lurched from one idea to another as we've tried to grapple with the cosmic acceleration. And so there's, I mean, already in the 90s, Steve Weinberg was wrestling with anthropic arguments to do with lambda, and if you asked him then, he was very unhappy to be doing that, but he felt we've tried everything and now it's time to look at that. Meanwhile, as these exciting results emerged at the turn of the millennium, we heard from string theorists that really lambda is going to have to be 0 because of supersymmetry, and we're going to have rolling scalar fields. Then the landscape burst on the scene, and people started thinking in anthropic terms again. Now we have the swampland pulling us in another direction. We have modified gravity. Is modified gravity the way to go? So we're just really grasping around in very different ways, which I think is exactly what we should be doing when we don't understand something. So it's nothing to be ashamed of. I think it's a tribute to people's adventurous spirit that we're trying all these different things. And another thing on my list is just what is a quantum description of de Sitter? And there's so many different ideas out there about that, and so many different ways people sort of prioritize what they even mean by trying to talk about that. And so it's just fascinating. I find it really exciting. I think we're still waiting for exciting new ideas to come in. And so I actually wonder, so is Eddington here? No. And then actually Lloyd has left, I know, but Rocky's here, which is the best we can do. So you're not. It's very good. We'll see. Right? So when you don't believe data unless it's confirmed by theory, what are your standards for that theory? Is it just a phenomenology, or do you have to understand things like the vacuum energy for it to count as a theory? And I don't quite know the answer to that.
It was confirmed by my theory.
By your theory. That's actually a common theme in this cosmic acceleration world. and other worlds we visit, yes. But to me, it's just fascinating that we have such a disruptive kind of data about the universe that's dragging us into all these difficult questions. And chatting with Glenn Starkman last night at the Blues Club, he said, but come on, we really knew we had to solve these problems anyway before we found the acceleration. And that's true, but I think maybe the acceleration simply put a spotlight on these things and maybe invited theorists to wrestle more openly with these difficult questions. So I very much like Rachel's emphasis on how we struggle to understand hierarchies, and maybe we're just thinking the wrong way about hierarchies, and I agree with that. I think we're finding ourselves confused about the things I just mentioned, about what we are learning from the LHC, about particle physics, and I think some of the questions I have that I mentioned this morning about the initial state of the universe also falls into that area. So the huge variation in the entropy of the universe from the early stages till today is another hierarchy of an interesting sort. One of the things that informs, so that's laying out the big picture, the challenges. Just a little mention of something that informs my own thinking about this. I'm also really intrigued by non-locality, actually in a seemingly different way from what you mentioned, but I find some of the issues to do with cosmic initial conditions I find intriguingly, I don't think we'll understand them with local field theory. I think there's going to be aspects of the initial state of the universe that will always look fine-tuned in the context of the phase space of the local field theory. But non-local ideas, the emergence of locality, might shed some interesting light on that. I think we're learning to ask interesting questions about non-locality when we think about the quantum nature of black holes and the horizons of a de Sitter space or during inflation may sort of import some of these ideas that we're thinking about with black holes in very interesting ways. So I think there's lots of places to find new physics and perhaps radical new ways of thinking about these things. And so I'm glad various people are thinking about that, and I'm definitely one of those. Coming back into observational space, so that was a very theory kind of perspective, I do want to reiterate this point we've already heard on this panel, that the difference between W exactly equal to -1 and any significant measurement different from that is absolutely revolutionary for the theories. So we can debate exactly where we draw the line, how small is small enough, but if it's statistically significant, if you actually get a measurement different from -1, it will turn everything on its head in the theory world. So it's a very exciting thing to aim for as we consider our experiments. And just generally, yeah, I don't know, this is sort of, again, a philosophical point, but Simon kind of presented a skeptical view of what all these theorists going around worrying about all these big highfalutin theories. We just have lambda and we're happy. I want to just reflect a little bit on theory questions as drivers. I know Alan Guth shares his experience going to a talk by Robert Dickey about the puzzles, the tuning puzzles of the universe, and how that informed cosmic inflation, which nowadays is making observers very happy. and so we should, I don't think there's really a need to defend this. I think as science as a whole, certainly cosmology, you coexist with people thinking wild theoretical ideas and questions and people trying to pull us down to earth and make measurements. But we've certainly got plenty of both here, so it's a great thing. I'm happy to be part of the adventurous theory side of all of that. Yeah, so we're at a very exciting time, and I think the theorists should keep adventuring, keep trying to solve these difficult problems, not be too narrow, not just find another scalar field, but ask how it really fits into these big questions, and the observers should build great experiments and keep us honest. So, over the floor.
So let's see, I guess I'm picking up the observationalist, experimentalist side of the panel here. And I thought that maybe I should begin with just the word of encouragement that well, remember back in 2000, when we were busy talking to every theorist we could find to try to get them to tell us, okay, so what should we be measuring now that we've seen the acceleration? What should we be measuring to actually tell why is it accelerating? And including Andy next to me, and we were not only trying to look at all the different theories, but we were also trying to look at the categories of theories and the meta-categories of theories, and just ask, are there any things that we can distinguish? And it was very clear, I'd say, at that time, that any theory we looked at, and any theorist we spoke to, the differences between the theories and the differences between any theory and cosmological constant were too small for us to be able to distinguish with the current measurements. Not only that, but the differences actually looked like they were too small to be distinguished by any measurement that didn't do a dramatic step forward. So it looked like you could maybe begin to see some differences if you got to 20 times more precise than we were at that time. And so this motivated a number of us to start developing projects that could actually have a chance at getting that 20 times reach. And I thought that was, and that's actually been one of the stories that's really been advancing. But I remember at that time having this little worry, which was that obviously we were going to be doing other projects along the way that were not going to have that 20 times reach. And every one of these other projects would end up coming back with this great discovery that they're consistent with lambda. And I realized that could depress the field after a little while, and that I probably should have written down a sort of some sort of wall chart saying, whatever you do, don't worry over the next 20 years or whatever it would be. If you're doing measurements at this level and you keep getting lambda, that we haven't yet tested anything yet. That's what we will expect to get for the next period. Now I was hoping it wasn't going to be 20 years. At that time I was still optimistic that we would have flown SNAP in 2007. And that there were other projects that could have come up sooner. But that's not the way the world usually works. Everything takes a little longer than you were originally hoping. And there's certainly a lot to be done during that period while we were building these projects that could get this 20 times more precise result. But so today, when we're just about to begin to see the very first of these experiments that does have that level of precision turning on, it feels to me it's the absolute wrong time for everybody to be depressed and beaten down by all these lambdas that we keep seeing in these different projects. And so that's my word, if that counts as encouragement. I just want to express this idea that we shouldn't yet feel like we've done that next step. But I do think that we're about to make that next step, and there's absolutely no guarantee. We still haven't found a theorist yet in the room who will tell us that they will stake their reputation on this next measurement that we make. They should either see it or not. And we know that it's possible that it's going to be several 20s that one has to go if you're going to see it apart. On the other hand, cosmology is still a pretty young field. And it doesn't feel to me like we've done that many steps without seeing something interesting. So we're about to take the step which I was hoping we would take a little bit over, but that we're about to take that big step forward. And I don't think it would be crazy for us to see something interesting. That seems like a not unnatural thing to occur if you take naturalness in that tone of voice. All right, so that's the starting exhortation to optimism and also just to keeping working on these projects and taking them those next steps forward. All right, so I also want to say, and by the way, I should say I was glad both for the cautionary notes from Gary that we heard earlier today from those who were downstairs. He gave a nice list that you saw on the screen there. And then also for the fact that at least one of the presentations expressed that same future optimism in Chiwe's presentation. So thank you, Chiwe. All right. Meanwhile, it's not like we were sitting around for these, since 2000, just waiting for these projects. There's been a lot of stuff has happened. A lot of good, I think really important steps have been made. And some of that has been a matter of refining and improving techniques that we already had in hand. But a lot of it has been taking techniques essentially from scratch and putting them onto our map. So, for example, I remember an early conversation about this possible technique that I don't think was yet named BAO at the time. And today, not only are we getting measurements with BAO, but we're about to make, probably it's the one that'll usher us into that next stage of precision first with the DESI project that's about to go online, as we heard earlier today. I think in my own field, if we have time, I can spend an hour on it. We made real advances. I think we definitely understand all sorts of things about how to make a precision measurement with supernova in a way that's competitive with the new bar that's been set by BAO, which is which I think is a pretty tough act to follow or to be part of. And it's because I think we've done a number of generations of projects with supernova, and we now understand things that you have to calibrate for the instrumentation, things you have to understand about the supernova. You can't treat them as if they're just one big class of type 1A objects that you're going to use. And if people are curious, I can tell more about that later. I will say, though, that one of the things that I might want to come back to later that worries me is that often we've learned things and we understand cautionary notes, like the ones that Gary pointed out today, but we don't necessarily yet have good, strong ways of building them into the projects when somebody points out that it's going to be a little bit expensive to build it in. And I would certainly recommend that people think very hard about the idea that if we are doing this next generation of projects, we just have to be willing to face the costs of doing it right. And that if we know something that needs to be measured, we should try to make sure that we can measure it if we have the ability to do it. All right, other improvements. We dramatically a better understanding of the issues of the hard parts and the parts that we now can handle for weak lensing. Photo Zs are obviously now we both understand more about what you can do with them, but also about the problems for Photo Zs. I'm very excited that we're now getting new techniques onto the table, even just in the last few years, so that the strong lensing is now giving you just a few measurements. I'm optimistic that we'll be getting tens and hundreds of measurements of those very soon. Clusters, we haven't quite brought them into our fold of active projects that are giving results, but we now know much more about what to do with clusters. And then even the idea that we have one example of a standard siren is just amazing. And in 2000, that was still a time when it was just incredible to think that we should be able to make those kinds of measurements. So, so these are great advances in the 2000s, since 2000. And I should even just mention that there's the possibility of even doing an occasional lab experiment. So, for those people who are following the chameleon dark energy models, it's kind of fun to think that we've really actually constrained a good fraction of parameter space on the chameleon models just by a lab experiment using a suspended neutral atom trap. This is the Holger-Muller experiment, plus put together with the old EPFOS torsion balance experiments of Adelberger and company. It's the idea that we could actually make a measurement in the lab that would be relevant is just fun to think about. I'm also looking forward to understanding the lithography measurements that Greg has been talking about. All right. I also want to point out another whole category of big steps in the field that have come in from the analysis and reduction side of the story. So as an experimental observationalist, it's interesting that it's not just the measurements that improve. It's also how we handle the measurements. And a number of things have changed since 2000. We're now routinely making our, calculating our error bars, which is always the toughest part of any measurement. Calculating the error bars by simulating, many hundreds of versions of the experimental data so the synthetic versions of the data then provide you ways to get error bars, and that's probably just an artifact of Moore's law that we're getting the capability of doing that on computers. But that changes a lot about which kinds of experiments you might consider doing because you feel you might be able to bracket the errors when you make the measurement. It also comes along, interestingly, I think, with a tendency to use much more of the Bayesian approaches to understanding your uncertainties and understanding your measurement in general. And we've done a big sea change in terms of to what extent we're willing to accept a Bayesian analysis, or to what extent we actually prefer a Bayesian analysis compared to a frequentist analysis. And that actually changes a lot about how we do the science, partly because it makes it easier to incorporate a very heterogeneous sets of data into the same analysis. And that it was much harder to do that without a Bayesian analysis. I will say that it comes along with a downside, which is that in the frequentist analyses, I think people spent much more time parsing where every uncertainty was coming from and where each source of the problem was. It's much easier to have it all hidden under the rug of a Bayesian analysis. And so I think there's a little cautionary note that many of the things you're now seeing come from an analysis that nobody could really explain how, why do we end up on this part of the parameter space? And it's because it's a very complex combination of how all the priors pushed you with all the different terms that you were fitting simultaneously. And so there's something that we should remember to go back to and keep in mind as we're accepting these analyses. Same thing probably should be said for machine learning. I don't think machine learning has yet been used for in our field for things that affect the actual parameters you get at the end in a direct way. They tend to be used more for selecting your which category of objects you're going to follow or study. On the other hand, the more machine learning comes into the picture, the more we have this danger of black box analyses and a very difficult time understanding where did things come from, so that we can back estimate what study should we do, what should the next experiment be. So just a note there. I think we've also been seeing a dramatic sociological change in how experiments are run and analyzed. So the collaborations are not only larger in the field, they also have this the open science and open collaboration. Philosophy is become a very big part of our world, open software and open analyses. And I think that's been a major step forward, and we've been able to do much more because of that. It also, I think, forces us to have a bit of a word of caution for a few reasons I want to point out. One is that because we're now doing a few of the things we always wanted to do, which is make it possible for people to use an analysis tool without having to rewrite it and reinvent it. It means that many graduate students, postdocs, scientists are ending up picking up a tool and all using the same tool that somebody else wrote without actually going back to first principles and rewriting it to the point they understand it. And so there are many more black boxes in these chains of analyses. And I don't know whether we've yet been hurt by it badly or not, but I'm a little worried that we wouldn't know it if we were hurt by it badly. I would ask, how many people besides George in the room could actually tell us, exactly where how you derive the number, let's say the Hubble constant we were talking about yesterday. These are really hard things for any one person to understand all the different elements that have gone into the story. And I think it's becoming a little worse just because we're also tending to use each other's tools in the way that we always hoped we would. We didn't want to have to reinvent the wheel. But now maybe we are all riding the same one wheel too often and not having several copies of the wheel that different people had built, so that we could find out if one of them wasn't true. Another big positive, I think, is blind analysis coming into our field in a big way since 2000. And for me, I think that's been an amazingly important introduction. I was really thrilled to see that's the way, for example, the recent strong lensing work was done for the Hubble constant. And the reason I want to highlight it is because I don't know whether other people have had the experience now, but I've now a number of times gone back to old data sets to reanalyze something, either my own analysis or other groups' analyses, and been shocked to discover that there were bugs in these analyses. And even more shocked to discover that the bug exactly canceled some other update that happened since then. So we got back the same answer that was sort of the one that people expected. And I've seen this enough now that I've come to a new position, which I guess also George yesterday made the comment that he must have had a bad childhood because he doesn't trust anybody else's analysis. I think I must have had a worse childhood because I don't trust my own analyses anymore unless I've done it blinded. And because I've really started to see this and I think of myself as a very honest scientist, and I think the others are honest scientists, but it's amazingly hard. The more complicated these projects, analyses become. And I don't know almost any project where the analysis is as simple as take 12 numbers, divide by 12, and there's your average. Everything now has computer programs that have to be debugged. Science has to be debugged. And so I've come to the point that I just don't trust it, and I don't trust myself without without the blinding. So everybody ask each other, is there anything we can possibly do to blind something before we do any of the next steps? I think it just could make a huge difference, and I always pictured what would it look like if we'd gone through the entire 70s with Sandage and Doppler doing the Hubble constant measurement, both blinded. I think it just would have been we would have been, I know the field may have moved faster, 20 years faster, if we'd done that. It sounds often as if it's going to slow you down. I think it's actually the way to speed things up. All right. So finally, and I'm assuming I'm still on my finally, there are just a couple of other parts of the story that I think I wanted to bring out that have happened since 2000. That as a observationalist, experimentalist, I think are just fun to think about. These are the tensions that appear, and the places that we think we see something that just looks wrong. And we've had a number of those. I mean, people have been worried and then not worried about. So we've been worried about the low L part of the CMB. But I don't think there are that many people right now, maybe a few people do it, but there aren't that many people right now who I think are feeling that that's a real driver for their work. Sigma 8 has tensions, as we were hearing about today. There was the Lyman Alpha Forest BAO measurement at redshift of 2.3, where people worked really hard to figure out how to get rid of that tension. And eventually they start thinking, well, maybe it's just a fluctuation, but I think there is still a case to be made that those things are still out there, and they could reflect, they could be meaningful when the time comes. And then of course today, yesterday, we heard a lot about the H0 current tension, and if we have time afterwards in the panel, I'll give you my impressions of that particular one at the moment. But what I want to say about all these tensions is that even though I think in general they're likely to go away just by the nature of regression to the mean when you've been hunting for anomalous tensions, you're bound to find some, and then they will regress to the mean eventually, and then you won't have to worry about them. Even if that's true, and then of course we have the occasional hope that some of them will be really real. But even if the ones that aren't true, I realized that my first inclination was to tell everybody, I was worried that all the theorists in the room were getting overly concerned about a latest tension. Let us experimentalists work on this a little bit longer. We'll tell you when we're ready to worry you about it. But then I started thinking maybe that's not the right answer. Actually, each one of these gives a chance to focus attention on some aspect of the work, either the quality for the experimentalists, the quality of the reductions, or the quality of the analyses, or the little places where things could have gone wrong in those, or for the theorists, the small actual phenomenological reduction of the theory to the actual prediction of that measurement. Could there be something wrong in those steps? Could be a bug even in those steps, or could there be something grand about the theory that we've learned? That they should be kicking the tires again and trying out. And in some ways it's really hard in these fields that we're in to get the motivation to go and do these deep dives into trying to figure out what are the pieces looking like. And so each one of these anomalies, each one of these surprising measurements, I think has really been quite good for us, because it's actually given us a chance to go back and do a deep dive in even just one little part or another part of the structure that we've been building. And so I've decided I'm not going to save the theorists all the trouble in the future. From now on, I'm going to make every one of them sound as scary, but make everyone sound as scary as possible. Just as we need things that will get us to focus, on some of the elements along the way. All right, so those are the things I was going to point out from the 2000s. And then I was finally, as the experimentalist, I was going to turn back to the theorists and ask the questions that we've been, that us experimentalists always keep needing to ask, so that we can design think about what do we design next and how do we build next. And some of them were the questions that have already been addressed, but I'll just list some of them again. One that I think was implicit in what you both were saying is the question of, is there any reason that we could be at all less concerned about the cosmological constant solution today than we were as physicists in 2000? That it's sounding to me from the things you're saying that we've played with many of these ideas a number of times, but that maybe we are, all the concerns about it are just the same as they were before. So if I was worried about it then, I should be worried about it now. So that's one. Another, which is probably a sub-part of this question, is where would the theorists find themselves feeling they are about the anthropic arguments? As an observer experimentalist, for me, it always felt like it was giving in, and that if I took the anthropic arguments seriously, in the 14th century, we wouldn't be here today in this room, discussing physics, in the way we are. But I'm always just curious to hear, how's it settling in for in the theory world. And then, of course, I'd love to hear more about the, where is the swampland arguments, playing with those. And then maybe, the other question was, does the comparison to the previous epoch of acceleration, the inflationary period, is that the red herring, a complete red herring, as I've had some theorists tell me that it's just, it's an acceleration and that's nothing to do with this acceleration? Or are there things that we could, as observers, that it might give us some guidance of something to do, because of that? All right, let me leave those questions on the table and pass back to the ball.
Thanks to all three of you for stimulating remarks. I think I want to sort of take off on some of Saul's questions. So I think these are some of the same questions, and I want to give our panelists a chance to address some of the ones Saul raised, or any of these. I think. I guess, so I think, Rachel, you started with the cosmological constant and talk about it as this problem that we still don't understand. I guess the way I think about the cosmological constant problem is, if you're, right, so if you teach like high school math or even college math, right, you give your students a problem, often, they don't quite understand what the orders of magnitude of the answers should be, so they'll get the answer wrong and they won't realize it's wrong. But I think, it's really hard to make a math error of 10 to 120, right? You really have to try hard. And even most elementary students would realize that they probably have made an error if they were off by that much. So I think Andy, I think you both raised this point. So I guess the question for both of you, following on Saul's point, is, how much do we have to worry about this elephant in the room when we're thinking about dark energy models, surveys? Are we confident that somehow whatever solves the cosmological constant problem, which again, as you said, has been around since long before the discovery of cosmic acceleration, how should we be feeling about whether that's orthogonal to what we're trying to measure, or is it intimately connected to? Do you have, and are there any theoretical is there any theoretical guidance for how to think about that?
You're looking at me.
Yeah.
I'm happy to say. So I think it's totally the elephant in the room. You do expect the theory to. Should I turn on?
Yeah, just turn on.
There we go. Okay. Yes. And the thing is, it's a hard problem, and we've wrestled with it and not yet solved it, or at least not solved it where we're convinced we've solved it. Sort of a version. I used to use the term the ego test. So if someone walks up to you and says they've solved the dark energy, it's because they're on the paper. And so the measure of when there's progress is when they're talking about someone else's paper. And nowadays, maybe we're into a little group, so maybe there's been some domain formation, and maybe that's a sign of progress. I don't know, but we're definitely not in agreement about what forms a solution. I think I'd make a distinction. I think it's a really hard problem. So sure, we should try to make incremental steps, sort of grasping onto whatever we can, and maybe we don't think about it all the time because we can't manage it, but we should keep it in mind. And I think in terms of observations, it's hard for me to imagine that getting in the way of the observations. Though I think the observations should just do the best you can, and not be certainly not slow down because of some random theory of the moment. I actually have comments about two of Saul's questions. Can I say anything to that? So, about inflation. So, there was a time when people thought, there were arguments made by theorists that you couldn't accelerate the universe, that there was instabilities that were fast and they prevent you from having acceleration. And that was actually a threat to inflation. So the fact that we see acceleration now is good news for inflation, because we know nature is capable of accelerating. So at some very fundamental level, that's
backwards.
Yeah, backwards from what you were asking.
Right.
And then I'd say there's a long list of reasons. I've talked with various colleagues here. Ways we can think. The de Sitter seem to be approaching now. How do we compare that with inflation? Are there interesting features from logography or something that impact both the inflationary area now? But I can't give you a soundbite about that. I think it's extremely interesting, but in the nitty-gritty. I also want to offer something radical, which is a moderate view about anthropics. I think we can actually all agree on something. So I like to describe, so there's this bin of all the data we have, and what we do with that data is we take some of it and put it into our theories to set parameters, and then we turn the crank on our theory and produce predictions, and we compare it with the rest of whatever data is left in our bin, right? And I think everyone will agree that if you can use less of your data to set the parameters of the theory and leave more of it behind to compare with your predictions, that's a better theory. I think we'll all agree with that. I think if someone comes up with such an improvement, people won't hold back and say, no, I really like putting more data in at the beginning. So I think there's actually agreement about that. And then the passions around anthropics have to do with how much because we don't actually know where we're going to go with that. And so the passions around anthropics surround the fact some people think we should be putting more data in, and then people get polarized and say, those people seem like they're giving up, and then other people claim the anti-anthropic types think you can put no data in, and so it gets very messy. But I think the culture of science will be to avoid anthropics as much as possible, and we don't know what that as much as possible is at this point. It's not absolute. It's an uncertain thing.
I guess I wanted to make one comment on that, because I think the plot, Rachel, that you showed of the hierarchy problem and the fine-tuning of the Higgs and then these other regions sort of reminded me that potentially you could believe in a misanthropic principle, right? Which is that, in most of those universes, if most of those universes are inhospitable, and if sort of the distribution is peaked far away from hospitability, then you can imagine that in fact we should be in a universe which is right on the edge of being able to support us. So you would predict that life is nasty, brutish, and short.
It's the worst of all possible.
Yeah, it's the worst of all possible worlds that we can live in. And so that may be true. I don't know, but
That's only the last few years of politics.
Okay. or maybe it's just I feel that way. But so anyway, but I guess I wanted to ask Rachel if you had any comments on possible connections or lack thereof between the cosmological constant problem and dark energy.
Yeah, so I certainly agree with what Andy said earlier, that if we do measure a W, it's not -1, that would be revolutionary. And then maybe that in and of itself is compelling enough reason to keep searching. But I have to say that in the opposite direction, that if observers keep measuring W equals -1 to more and more accuracy, I think I would have more and more questions about whether the cosmological constant problem is really a problem to begin with, or whether it's something that we haven't understood correctly about field theory or gravity.
Okay, so that's interesting. You're saying that actually dark energy experiments could maybe tell us how to think about the cosmological constant problem.
That's from my point of view, yeah.
Okay.
Would you have had the same guess that I had that looking at it from several years back, that today we wouldn't be able to tell apart yet, so that it's really, you really need to be doing something where there's some degree of strength before getting the measurements over and over again without it.
I mean, I think my bias is probably that the cosmological constant is just a cosmological constant. So I think my expectation is that we may never measure it as different. But if you're not allowing for that, then yes, I guess I would also agree that probably it would have taken some time to measure some discrepancy.
So given that bias,
Yeah.
but how do you feel about quantum field theory?
Concerned, but interested. Yeah. No.
There's tension there.
No, I agree. I agree that there's definitely an open question, but I'm not sure. I'm not convinced that the resolution will be in something that takes us away from a non-dynamical form of dark energy.
Actually, so I wanted to probe that a bit because Saul raised this question of whether comparing the current epoch of acceleration with inflation was a red herring, and so in fact this is not the first and cosmic acceleration. This is the second one. There was one 10 to the minus 35 seconds after the Big Bang, and we had a distinguished panel of people here just at the dawn of inflation, and we asked them, okay, why is the universe starting to accelerate? And they all said, oh, of course, dummy, come on, it's the cosmological constant, of course, what else could it be? And then, at least 60 e-folds of inflation later, or more, they would have been proved wrong. So so that's an argument I like to use against the theoretical prejudice, but it could just be a red herring. So is there and you talked before about hierarchy problems, which somehow seem connected with this as well. So can you talk a bit about sort of what's behind your bias?
Yeah, I mean, I certainly think it's a very reasonable argument. You're saying, look, we know that we certainly expect that the universe already went through some epoch of accelerated expansion. Why should we think that the current epoch of accelerated expansion has nothing to do with the previous one? And I certainly think that that's a valid argument. So I don't know, I might have to think more carefully.
But you still have a prejudice that's
I have a prejudice that it should be the simplest model that fits should be the one that we are biased towards. Not that it's the correct answer, but that's where I would place my bet, would be on the more simple model that fits the data.
Even though that would have been wrong the first time.
That's correct.
By the way, half the time I have that bias too.
Okay.
Because I like the finite universe it creates.
But Josh, would that have been a good argument back then? After all, back then the vacuum energy you're talking about would have been much bigger than the electroweak vacuum calculation.
Yeah, but it was still well below the Planck scale. Right?
Well, but it wasn't that. I mean, it's nothing like that.
Right, but so then you're invoking a hierarchy argument that somehow.
Slow roll.
that somehow, if it was relatively close to the Planck scale, then it could be dynamical, but somehow we're so far below it that we must have reached the bottom, right?
W would only been off by 1 part, in 60, wouldn't it?
No, it would have been measured,
qualitatively different.
would have been within a fraction of a percent. Right? Yeah.
No, not necessarily.
No.
Why? You live on a Hubble, I mean, do you live a Hubble time now? Why would you live a Hubble time then?
No, we do up to date, sending over Hubble.
Right, George?
No, I mean, anthropically, that first phase had to win.
Sorry?
Anthropically.
First phase had to win.
Well, but if you had been around 10 to the minus 35 seconds after the Big Bang,
How would you know?
you would have made the same argument. Now, you would have taken a slightly different form. Yeah. And, okay. Yeah.
So-
Let's.
All of a sudden it's George's.
Yeah. Go ahead. Rachel.
So in fact, I wanted to respond to one of Saul's questions about anthropics, which was, if I understood correctly, sort of at what point do we say, okay, in a sense, give up and say, well, it's probably anthropics. I think that things can be done to put the anthropic argument on a more solid footing before we get to that point. And so I think these questions like, are there, metastable de Sitter vacuum and string theory? What is the mechanism for these vacua to get populated? Is in fact string theory, the unique UV completion of a massless spin-2 field? I think before we sort of say, well, it must be anthropics, I think there is theoretical work to be done to make that a more compelling and more
In other words, what you're saying is that the current state of the theory has enough loopholes and weaknesses in it that those have to be shored out first before you start feeling like, well, the anthropic is an argument.
That's right.
It's
It's a
still not, it's
scientific
still not
argument.
yet there an argument.
That's right.
So, sorry. So George does have a question.
So I think that, this, if you can't define a measure, you can't do anthropics. So I think
We can't define a measure.
exactly.
Yeah.
So I think it's,
So we're not even really doing anthropics yet.
Exactly.
Right.
I guess the other possible way that anthropics would turn into something a little bit different than my fears would be if one had a landscape model of some sort that had this good anthropic arguments, but it also happened to be able to make some other prediction of something that we haven't measured yet, but that we can measure, right? And at that point, then it turns into something different than a snowball.
But even then, if you had a more predictive theory,
You might still
that
go
would
for that.
draw the attention. Yeah.
So speaking of lack of measures, I want to maybe ask about the third point, which is, as far as I can tell, we don't have an agreed upon theory space to talk about dark energy, or at least a measure on that space. So this always leads to the question of, how far should we be going? We're now transitioning from stage 3 to stage 4. As I mentioned, in principle, at least in principle, there could be a stage 5. Our opening speaker has questioned the wisdom of spending large sums of money and large amounts of your energy in mounting such projects. And so I guess I wanted to ask the panelists your views on this. Do we wait until we see what comes out of stage 4, or is that going to be too late to think about whether, obviously, if we see something different from Lambda CDM, we would want to continue. But if we have to wait for the stage 4 results before making that decision, it's going to be our children's children who will be doing stage 5. So I wanted to get your thoughts on that.
I mean, I think anything we learn, again, could be revolutionary. And for me, that might be sort of the most compelling motivation to go forward. But I think motivating it from a theory point of view, from like a specific model or a specific theory, it's much more difficult to say, well, we have this very compelling theory, it predicts this, and therefore we should go out and find it. I think that's a harder argument. So
maybe let me ask you unfair questions, which is you have your theoretical bias from that, so you've got some prior.
That's right.
And then what kind of experimental posterior, how narrow does that have to be before you multiply those two and decide that your Bayesian odds are high enough that it's not worth spending another $500 million or $1 billion? Which is a totally unfair question.
I mean, yeah, so maybe since it's unfair, I can invert it a little bit. And I think if we had some other form of evidence that, you know, maybe we detected equivalence principle violations in some other sector, maybe we detected fifth forces somewhere else, then maybe that would, you know, sort of renew interest in pursuing this. But yeah, yeah, it's a hard question.
I don't know if Andy or Saul,
Yeah,
you want to
I'll say that I think in practice, these decisions are made about projects that are of interest not just to one narrow question, but a broader community. And I think to the extent that that's going to influence, so what kind of coalition can you build around a particular project? And in my sort of ideal world, you do things that have obvious, concrete contributions to moving the science forward, along with these big questions that may, you know, where you can't predict, you know, what step is the right step to take. And you've got to do both. I mean, then there's examples. You don't always find the perfect blend in a given project, but overall you do that. I mean, look at the story of the gravity waves, right? That's quite a story of one extreme, and there's others. You know, you built the LHC because you promised that you'd find the Higgs. So there's, or supersymmetry, or whatever you promised to find. And so there's, and as part of it is the culture. We made the case for stage 4 based on this figure of merit. But, I don't know if this is the right moment to say, but I think it's a very weak statement. Compared to what these things can really do, it's a very, very weak statement of what is possible. But somehow it took off, like, miraculously. I know. But Gary and I wrote a paper that explained, anyway, I can tell stories about, like, how little people questioned it, and then the moment on P5 when people said, wait, we're going to spend $1 billion to do a factor of 3. and then I showed them the paper with Gary, and it's not a factor of 3. But so the whole dynamic of how we make these decisions is a big sausage being made, and so. But I'm happy to pipe up for the dark energy interest along the way.
So maybe I would like to open it up to the audience, because if there is going to be a stage 5, then I think it's actually all of you in this room who will be the ones really convincing our colleagues and the community and our governments. But so I guess I would like to get a sense of if people want to comment about whether you think that stage 5 is extremely well known, that we should be planning it now, or should we be? You know, we all have plenty of data to chew on with stage 3. The next few years with stage 4. Should we just go back and analyze the data? So I wanted to get some thoughts on that. If people have comments.
I think part of the answer to that is an answer that Saul is going to give to a question I have. So if you compare searching for dark energy to, say, nuclear recoil in direct detection of dark matter, there is a neutrino floor, and it's a game changer if you get to there. It's going to require new techniques, something really different, make it much more difficult, much more expensive. It's not just incremental once you get to the neutrino floor. Do you see anything observationally that's equivalent to the neutrino floor in looking for W or WA or searching for departures from lambda?
No, man, it's a good question, and I don't. It's not like I would immediately say, oh, we know, if we get to this level, we're now actually exploring a whole different kind of project. The closest thing might be that we know that there are other side projects you can do where, let's say, if we really understood the local peculiar philosophy, we would actually now be studying something about neutrinos and others in ways that we hadn't done before. But not for these projects that we're talking about right now. I guess I tend, just getting back to the bigger question, I tend to go the same direction that Andy's going, that you have to come up with a broad enough constituency. But I guess I also keep thinking that from the observer and experimentalist point of view, our job is to constantly be looking for something that just all the theorists are saying, but we've never actually measured it. And that it's actually worthwhile making the measurement for something that we all know should turn out to be the case. If you make that measurement, because often when we've done that measurement, it hasn't turned out to be the case, and that it's we have to somehow manage to balance listening to all of our theorist friends enough so that we get pushed in the right direction, but then be willing to say, okay, that part there, we just need to measure it anyway, no matter how many of them say that they know what we're going to get, because it's just part of the groundwork on which we should all be building. We don't want to have too many parts that are theoretical all the way up on too many levels. We sometimes need to shore it up with a measurement along the way. So that was the only other one I was going to throw in, that I think we should.
That increases the impact if you get something different.
And of course, right, then it's even better.
Dumped over the whole tower.
Yeah.
So I had the impression my name's being taken in vain as a bad guy here, but I don't actually think we have a disagreement, because answering the question as Josh put it, of what precision should you be aiming for and can we afford it, I think the answer is clear. You should go for the highest precision that you can afford. And that comes back to, of course, how much money have you got. And that depends on how much support you can get. And the way to get support, as Andy said, is to build a large coalition. So if this work is through astronomical surveying, which is most of what we're talking about, that support is probably going to come from other parts of the astronomical community. So you want to design your survey in a way that it will get the best precision that you can for the things you're trying to measure, but at the same time will serve other people's interests, like discovering that first might be useful for planetary science. That's a big step forwards in getting support.
Yes.
And I think one has to be thinking in those terms, because all these things are going to be, in the end, very expensive if you're really going to make a significant step forwards. And you can only do this if you have very wide support.
I wonder if anyone who's going to still be alive during stage 5 wants to. Any of the younger people want to make a comment? Or...
I'm at least younger than the people who have spoken.
And you don't need a microphone. So
I don't need a microphone. I'm really, I want to measure all the galaxies, all of them. But what is really interesting is that in principle, if you look at the curve of number of redshifts per time, we should get there in the 2060s. So to me, that's actually pretty motivating. That I don't want to do stage 5 based on the current dark energy figure merit. That doesn't sound very compelling to me if we haven't found something interesting. But sort of echoing what people were to say, measuring all the galaxies and everything we can about them, to me, that's really compelling. Even without me knowing what that's going to do for breaking specific models.
Yes. My position, or the way I see it, is that this is an answer to your question about stage 5. So is whether for stage 4, in fact, already, but also for stage 5 experiment. I think while approaching the question of cosmic acceleration and the cosmological constant, using the equation of state is a very important and a route and approach to understand the CC problem and the cosmic acceleration. But I think at the same time, the way the data is hitting, at the same time I think we should encourage strongly other approaches besides W, besides the equation of state. So in that case, those experiments will be designed not only to cover W, but also cover other ideas and other approaches. beside the equation of state. That's how I see it.
Actually, I'd like to answer Roddy's question to this whole. In fact, there is an analogy of this neutrino floor in the lensing of the B mode from the E mode in scene B. And still, the quest for the scale of inflation is sufficiently important that even though you know that you have to deal with delensing, you have to understand well all your systematics, you have to really lower your sensitivity, improve it in order to see it. It's worth it. It's really worth it to try. I don't know whether in the case of, so this has to do with the second panel.
That is a good example. Yeah.
But that's...
No, it's a good example. In fact, I think it also highlights something else that I'm sure everybody knows, but because we always make all those arguments whenever we're developing these instruments, and we have to excel to the congressman, that just being focused on a really, really tough precision experiment teaches you how to make all sorts of measurements that you otherwise wouldn't know how to make. And obviously it's a great story about why it is that this is also good for the economy, etc. But I think it's also a great story for what's good for us being able to do the next generation of experiments. I mean, that we often find that the best idea for a new experiment is one where, because so-and-so now knows how to do such and such that they did because they had some challenging problem, I can now do a different experiment that we always would have dreamed of doing, but we never knew how to do it before. And I think that these challenges that push us to the edge of our technical abilities to control things and to be able to make tight, very tough measurements, and these these B-mode questions are great examples.
Yeah, I guess my view on that is, as Gary talked about this morning, I think there are in fact many potential neutrino floors, analogs in dark energy. We haven't hit them yet, but we don't know if, there are many of them that could turn out to be floors. And in fact, my worry is that we're going to hit them in stage 4. And it's not clear to me, maybe other people feel more optimistic, but this is getting to the 4th bullet. It's not clear to me that we've knocked out all the systematics that we need to reach the accuracy the precision that is advertised for the stage 4 projects.
In fact, I was going to echo that when we were discussing the fact that we're using more and more of these statistical techniques to answer questions with very sparse amounts of data. And I think it's leading people at times to forget that you actually do better with real data than with some inference from lots of separate pieces of the story. And that we actually need to work on each of those, like Gary's list, with an attempt to get actual measurements that will get them, not just inferences that might be able to clean up some of the systematics. So I do think that's a really important element for our community.
Any other questions or comments?
I think whether we like it or not, the data people, we are very strongly influenced by the theorists. And so I'd like to not leave the theorists off the hook. I agree that it's very interesting to test whether W is -1 or not. But 20 years ago when this DGP gravity theory came out, it was so stimulating. All of a sudden observers realized we haven't measured gravity to even 10% outside the Milky Way. So I think there's a case to be made for the last bullet for throwing out some cherished notions like locality and Lorentz invariance. If you can persuade enough of your fellow theorists and offer stage 4 and stage 5 experiments, new regimes to look for signatures. Because the data is going to be so rich in so many dimensions that if we are just going after W, we are taking a very narrow view of the data.
Assignment accepted.
Hi. Yeah, just coming from a slightly different field of particle physics and collider physics, I think it would be good to encourage the theorists and the experimentalists to think a little bit of a diverse portfolio of measurement. If you take a lesson from history, it took about 20 years to establish Planck's constant as a constant, because when Planck did it, it was just a fitting parameter to black body radiation, and they could have kept on fitting it for 20, 30 years. But he was lucky, Einstein found the photoelectric effect, and then Bohr used it to explain the atom, so H all of a sudden became more than just a fitting parameter. It was a constant that was, so I think we should look for new types of manifestation of the dark energy and cosmological constant to have a diverse portfolio of experiments in the generation 5, rather than doing the more and more of the same thing, more and more precisely, and we don't get any more knowledge of it. So that's my comment.
So Rocky's telling me that we're out of time, so I want to please join me in thanking our panelists again. And, I have one quick announcement before you all adjourn.
Hi, so some of us were thinking of having a platform for junior members to sort of get together. Since tomorrow dinner is open, if you're a junior person, so grad students, postdocs, and you're interested in meeting other people in the same boat, please come find me. I think we'll just meet in this corner tomorrow after the panel ends. Thank you.
Reconvene at 3:40.
What is it in I haven't, I must admit, I don't have because I don't know how much of it is radiated out as they come to I don't have a good insight.
The only insight I have is that black holes that are used physically on those it's what's being extremely in principle, very rare you can get high speed, this sort of thing, and very rarely you get really high speed. So I would love to know what the speed is because maybe it's the only way to make an extremely black hole. And even if one of them is incredibly rare, nevertheless, you're making these things early, they can become relatively that's my interest.
We have done head-on things, so there's nothing but once we start setting them at an angle, at distance from each other, they should have, we haven't done that. But I would think that's essentially the question you want to answer. What is the max? The question you asked me, what is the maximum spin distribution?
It's the distribution, actually. I think would be really interesting to try and figure out.
Do you think you can get is your intuition that you should be able to get a very high spin?
Yes, why not? Why not?
But you think it's a hard thing to get? Is yours?
High spin has amazing implications. I mean, really high spin because it changes the lifetime of the spinning black hole. Right. Etc. They go more quickly, so that opens up the window of possible masses, changes that.
So I will certainly look at it. We are looking, we're asking, I think this falls into this general question that I'm trying to ask is, what is sort of the end state of collection of these lights? Some of them go to black holes, some of them go from particles, and this will be part of that answer. What is the distribution of these black holes? And I don't have an answer.
This is happening at the heart of the meeting.
Well, it can. We will be able to also do this to an extended action.
Yes.
But there it's a little bit more cute.
Or even before the meeting.
Yeah. This is happening at the end of inflation. overheated into anything.
That's right. It's a nice place where things are unstable.
Exactly, yeah. So that's one place we can certainly do this. We could also do this just in the axion field when the axion has been started to roll.
Sure.
So you could do it at that time as well to an extent. But here it's a little bit harder because the background expansion is radiation coupled.
Yes, yes.
So it's fast compared to this.
Sure.
But you can, a little bit of tuning allows you to still do it.
Sure.
So there it's a little bit harder. But I think if you wanted to get something which are large black holes, you would probably want to do this process of late in the history of the world.
Well, large, I am happy with asteroid size. I see.
But even asteroid size, I need the volume within the horizon, as you can imagine.
Sure, that's right.
So I need to be at that stage for it to be, so it would be late compared to gut scale and
Oh, well, of course, yeah. What sort of reheating temperature do you consider?
So here we did it because this is sort of the dynamics I showed was scale, didn't care about the scale, right? So it just depends on what scale you're willing to put this on. So it really doesn't depend on what scale. This was, I think at some point, you would also, you probably don't remember, but a long time ago we had discussed this about where these things that fit over there, whether they influence something about the void property. I think you were interested in void at that time, and I still haven't thought about enough to give you an answer, but it's, but this question about spins, I think, is an interesting one. I'll try to see if I can.
Yeah, so we wrote a paper recently on the effect of extreme spin, meaning full minute and even higher, having an effect on the evaporation products of the gamma ray background. We found that we could actually reduce the window for possibly really.
I see.
Okay. Which are 10 to 20 minutes, whatever.
I see. But thanks.
Sure, okay. Yeah. Enjoy your talk.
Yeah, thank you.
So I'm not going to work on it.
So
kind of